Hará la presentación el doctor Enrique Forero, profesor del Instituto de Ciencias Naturales de la Universidad Nacional de Colombia y presidente de la Academia Colombiana de Ciencias Exactas, Físicas y Naturales. Doctor Enrique Forero. Gracias.
Buenas tardes. Para mí es un honor presentar a nuestro siguiente conferencista, el profesor Serge Haroche. El profesor Haroche nació en Marruecos, se graduó de la Escuela Normal Superior de París y obtuvo su doctorado en la Universidad de París VI en 1971. En 1975 fue nombrado profesor de tiempo completo en la Universidad París VI, cargo que ocupó hasta el año 2001, cuando fue nombrado profesor en el Collège de France para ocupar la cátedra de física y la dirección. Sus investigaciones han tenido lugar principalmente en el laboratorio Castler-Brossel de la Escuela Normal Superior, donde ahora trabaja con un equipo de alto nivel entre postdoctorados y estudiantes de posgrado. El doctor Haroche ha recibido numerosos premios y distinciones, entre ellas la Medalla de Oro del CNRS en 2009, es oficial de la Legión de Honor de Francia, en 1988 recibió el premio Einstein, en 1992 el premio Humboldt, y en el año 2012 el Premio Nobel en Física, que compartió con otro de nuestros invitados especiales, el doctor David Wineland. La Academia de Ciencias de Suecia destacó en el comunicado en que anunció los premios lo siguiente: los premiados han abierto la vía de una nueva era de experimentación en la física cuántica al demostrar la observación directa de partículas cuánticas individuales sin destruirlas. Sus descubrimientos han sentado las bases de la actual investigación fotónica que aprovecha las propiedades de las partículas de la luz, los fotones, para crear nuevas tecnologías y profundizar en la comprensión de las leyes físicas. Con ustedes, el doctor Serge Haroche. Doctor Haroche.
It's a really great pleasure to be here, and I would like to thank Professor Enrique Forero for organizing this meeting and inviting me and giving me this opportunity to meet with Colombian colleagues and with students, and I hope that this meeting here and during the next days in Medellin will improve and strengthen the cooperation between France and Colombia and other countries. And I think it's a very useful event, and celebrating the Year of Light is, of course, also very, very important. I am also pleased to have this opportunity to describe, I hope in simple terms, the experiments I have been doing with my research group in Paris for many years. What we are doing is to trap photons in a box and control and manipulate these photons without destroying them. And by doing these experiments, we are, so to speak, I don't know what happened here. We are trying to realize some of the thought experiments that the founders of quantum physics have been imagining during the 1920s. And these experiments illustrate some basic concepts of quantum physics, and they also demonstrate steps which one day be useful for quantum communication or quantum information. Basically, we are manipulating photons, which are grains of light, elementary particles of light, and I will start by recalling a few features about the photon, which have already been, some of them have already been discussed in earlier talks by Alain Aspect or by Professor Boris Rodriguez. As you know, the photon has no mass. It flies at maximum velocity at the speed of light, and it's a very common particle. In fact, it's the most common particle. There are photons everywhere around us, in this room, of course, visible and invisible photons, and they carry almost all the information we have about the outside world. If you can see this screen, or if you can see me, it's because photons are scattered from my body into your eyes, and this happens for give us all the information about our close environment, but also all information about the universe. Visible photons are, of course, important in astronomy, but invisible photons are also essential. You see here, you may have already seen this map, which represents in false colors the light, the invisible light, the microwave radiation background that we receive from the universe. And the photons which have been captured in this kind of picture have traveled for billions of years since the early time of the universe, and they give us precious information in cosmology about the early days of our universe. What is also interesting to notice is that these photons are dead now. When you detect the photons, usually you destroy them. So the photon gives us a message about the world around us, but this message kills the photons. And of course, it's not so important because there are so many of them, they're always renewed, but the photons which have been detected are no longer there. Another feature, in free space, when they travel in interstellar space, the photons are eternal. They can travel for billions of years without any harm. But as soon as you try to capture them, to trap them, they are very fragile because they interact very strongly with the matter that you put around them, and they does not survive long in captivity. In the best optical fibers, the photons will propagate over hundreds of kilometers, meaning microseconds, but then they will be destroyed, they will be absorbed. What we are doing in our experiment is quite unusual. We observe photons which are trapped during times of the order of 1/10 of a second, and we can detect them repeatedly without destroying them. So we have developed a way to count the photons without absorbing them, and this allows us to perform the experiments I was mentioning before, controlling the photons, building non-classical states of light with them, and trying to figure out what could be done for applications. I just recall you what happens when you detect light in usual ways. The photoelectric effect, which was understood by Einstein in 1905 in one of the seminal papers which started all the quantum history. What happens is that a photon impinges an atom and it just ejects one electron, and in the process the photon is annihilated. So the photon is observed by detecting the escaping electron. And the same kind of process occurs in the ordinary vision. You get photons into your eyes, the photons interact with molecules, with molecules in the cells of your retina, and they are transformed by a photochemical effect into a signal which goes to your brain, but the photons are dead. So the question is, can we detect light without absorbing it? And I will tell you how we do that, but of course there is an ingredient which is essential if you want to do that, is that you need a good box to keep the photons long enough to be able to measure them again and again, not only to demonstrate that you have not destroyed them, but to be able to do things with these photons. And this is what our experiments are about. As I said, photons are quantum particles, and this has been discussed already in previous talks, but I would like to discuss that by showing you here the Young double slit experiment. In this experiment, which all physicists know about, a source of light is send photons, send beams of, this doesn't work anymore, send beams of light through a screen which has two slits into it, and then the light goes through the screen, and it gives rise to an interference pattern on a screen. This is, of course, understood very well if you consider that light is made of particles. Light is a wave, excuse me, because the waves which come through the two slits interfere with each other, and in some directions they add their effects interfere positively, and in other directions, one of the two wavelets has a phase which is opposite to the other, and they cancel their effect. But this is very difficult to understand if the photons arrive one by one. That is, if the source is emitting single photons, and this has been possible in recent times, and this is an experiment which has been done by Jean-François Haroche in Paris, and I show here the result of the signal of a real experiment. You see on this screen how the interference pattern will build up photon by photon as the photon arrive on the screen. You see at the beginning you have a kind of random pattern, and when enough photons have arrived, you see that the interference pattern is building up. So the photons tell us two contradictory things for a classical mind. They tell us we are particles because we give discrete impact on the screen, and at the same time, statistically, we are a wave because we give rise to an interference effect. So how can you understand that? The only way to understand it is that each photon, when it crosses the screen, in some way knows whether the two holes are open or not. And this means that the photons does not follow a classical trajectory. If the photon was going through one hole, then it would be able to hit the screen anywhere. If it cannot hit the screen on a dark fringe, means that in some way it crosses the screen through the two slits at once. And this is what quantum physics describe as a superposition principle. I won't write any equations in this talk, save this one. The state of the photon which crosses the screen is a superposition of the state corresponding to crossing through the slit X and the slit Y. This is a superposition principle which is at the heart of quantum physics and which is a direct consequence of this wave-particle dualism. The same dilemma exists, of course, for matter. Electrons, atoms, molecules are also waves and particles. This has been, for the first time, stated by Du Bois in 1923. And the superposition principle applies to matter. And this will lead us to the Schrödinger cat problem, the fact that a quantum system can be in two states at once. And I will say a few more words about this just in a second. This is, of course, the wave-particle dualism of quantum physics, and Bohr. Thank you. Thank you very much. This wave-particle duality was discussed by Bohr, who introduced the notion of complementarity back in the 1920s. I'd like to illustrate this by this ambigram, which you can read according to your frame of mind. Light is a wave or light is a particle. Of course, this is not just a psychological game. What Bohr had in mind is that the particle and waves are the two sides of the same reality, and which reality emerges depend upon the experimental setup, not about the way you think about it, but about the apparatus that you put to study the system. This means that you cannot prevent, when you observe a quantum system, the system from interacting and from being perturbed by the apparatus with which it interacts. Depending upon the experiment, the system will appear as a particle, which has a well-defined trajectory, or as a wave, which obeys to the superposition principle. And when Bohr discussed with Einstein in the 1920s, they tried to imagine experiments to put this idea of complementarity to the test. And one of the experiments was the modified version of the Young double-slit experiment that you see here. This is a drawing by Bohr. You see the two slits are here and there. And what Einstein imagined that the upper slit was a very light device which was suspended on two springs here. And what Einstein said is if you want to find the path through which the particle went, you just have to detect the momentum transfer to the movable slit. If the photon, for instance, is going through the upper slit, the slit will recoil and it will start oscillating. And if this slit oscillates, it means that the particle went through the upper slit. If the particle went through the lower slit, of course, the upper slit will not move. So will you see interferences? Will you see, when you accumulate photons, will you see fringes in this case? And Bohr could answer very quickly that according to quantum physics, the fringes should disappear if you do this experiment, because it will require to define the slit initial momentum with a very small uncertainty, delta p, because the change in momentum will be small. But if delta p is small, according to Heisenberg uncertainty relations, delta x, the fluctuations of the initial position of the slit will be large, because the product of delta x and delta p has to be larger than Planck's constant. So what happens in this case is that the 0-point fluctuations of this quantum oscillator will be large enough to blur the fringe because the path difference will no longer be defined. So Bohr was able, with this very simple thought experiment, to show that, in fact, the idea of complementarity was at the heart of quantum physics, of the principle of quantum physics, because Heisenberg uncertainty relations are at the heart of this physics. So it's not something that you add to the quantum theory, it's really imprinted within the principle of quantum theory. I like this experiment because it was discussed in 1927, and it already includes the notion of entanglement. If you think about it, if you look at the quantum state of the particle which crosses the apparatus, this particle has to be in a superposition of two states. It crosses through the upper slit, and at the same time, it crosses through the lower slit. But the particle is not alone in this experiment. The particle is interacting with the slit, and you see that now that if the particle crosses the upper slit will move, whereas if it crosses through the lower slit, the upper slit does not move. And from this expression, you see that the quantum state of the system particle plus slit is now an entangled state. Entangled meaning that you cannot write it as a product, as a mathematical product of a quantum state for the particle time a quantum state for the slit. So Bohr and Einstein did not discuss that in these terms, but entanglement was already there, and according to a modern description of this experiment, it is an entanglement between the slit and the particle which kills the coherence. And the explanation is quite simple. What this experiment means is that there is a quantum state for the global system, but there is no quantum state anymore for the particle itself. And if there is no quantum state for the particle, you cannot have any quantum coherence. And when you write down the equations and find out what's going on mathematically, you find, of course, this result. What I also want to say is that this experiment is already a Schrödinger cat experiment. The slit, which is a big object made of many, many atoms, is at the same time moving and not moving. And this looks very much like this famous cat that Schrödinger imagined, which was at the same time dead and alive. I just remind you here this Schrödinger story. You have a cat which is in a box interacting with a single atom, and the atom is in a superposition of two states, an excited state and a lower state. And if it goes from the upper to the lower state, it emits a particle which triggers a device which kills the cat. And if the atom is halfway suspended between the excited and the not excited state, the cat should be at the same time dead and alive. And it's exactly the same equation as for the slit experiment I just discussed. Of course, it's much more dramatic here, but the physics is the same. And what Schrödinger pointed out here is that as soon as systems interact, the superposition principle leads to quantum entanglement. And of course, it becomes rather strange when this entanglement involves a small and a large system. So it also raises the issue of the quantum to classical boundary. Why don't we ever observe this kind of situation when we look at large systems? So this is, I wanted to discuss a little bit these thought experiments. I will discuss last one here, which is related to the issue I was mentioning at the beginning. Can we count photons without destroying them? And in fact, in the 1920s, Bohr and Einstein had an idea about that, and they designed what is known as the photon box experiment. You know, in this experiment, they assumed that light photons were trapped in a box whose walls were made of highly reflecting mirrors. And the idea was how to know how much electromagnetic energy we have in this box without absorbing it through detectors. And Einstein's idea was just to weigh the box in the gravitational field of the Earth. So you see that you have here a meter which will go up and down along this scale if this box suspended to this spring weigh more or less. And of course, this experiment is based on the fact that mass and energy are equivalent. So if you have some electromagnetic energy in the box, you have something which will be sensitive to the gravitational field. This is general relativity. So to count photons without destroying them, you just have to weigh the box in the gravitational field of the Earth. I don't want to discuss this in more details, but I just want to stress that this experiment involves a clock here, that you can see here, which is used to control the opening of this shutter here so that you can time the exact time at which light quanta are escaping from this box. As was mentioned already by Dr. Boris Rodriguez earlier, Schrödinger and all the other founders of quantum physics, at least I'm sure Einstein, believed that this kind of experiment, these thought experiments were just kind of intellectual games, but that they will remain forever impossible. And we always quote this statement by Schrödinger, dating from the year 1952, saying that we never experiment with single electrons, atoms, or small molecules. We do that in thought experiments, but it always results in ridiculous consequences. At first, this sentence can look strange because in 1952, single particles were already detected routinely in cloud chambers, in accelerator physics, and so on. And of course, Schrödinger knew that. But Schrödinger considered that this was completely different from what we have in thought experiments, because what we were observing then were traces of events which have passed, which the particle that you see in these cloud chambers or in these collision chambers are dead. You just see the debris of collisions after they have occurred. And he said that very clearly when he went on saying that it is fair to state that we are not experimenting with single particles any more than we can raise ichthyosaur in the zoo. We are scrutinizing records of events long after they have happened. In other words, Schrödinger considered that particle physicists were like paleontologists, which were trying to make sense of a physical system long after the system had disappeared, just trying to find out what was going on through very long gone traces or artifacts. So things, of course, have changed, and now we can control a zoo of particles in the lab, and this has become possible because of new technology, of course. Lasers, and this brings us back to the International Day of Light, lasers which were first developed in the 1960s, and especially tunable lasers allow us now to control with an exquisite precision the internal and external degrees of freedom of atoms. Fast computers are essential if you want to accumulate data and correlations, in particular, which occurs at a very fast rate in this system. And in our case, we need also superconducting mirrors in order to build our photon cavities. And what I want to stress is that all these are quantum technologies. And they have allowed the ion traps experiment, the photon traps that I'm discussing now, cold atom physics, and so on. So you see that there is a very interesting connection between basic physics, between blue sky research and applications. It is because we understood the microscopic world that these technologies have emerged, and from these technologies we get new tools to investigate further and further and get deeper and deeper into quantum physics. So the kind of experiments we are doing is shown on this slide. You see here the mirrors that we're using to track microwave photons. We send atoms one by one between these mirrors, and they interact with the field which is stored inside. These mirrors are made of copper, machined with very high precision to avoid scattering on mirror imperfections, and they are coated with superconducting niobium, which brings the resistivity of these mirrors to zero and prevents all losses on the mirror surface. And with this kind of mirror, light can bounces more than 1 billion times between the mirrors, and if you unfold the trajectory of the light beam, the trajectory is on the average 40,000 kilometers, the Earth's circumference. So we have a little bit more than 1/10 of a second to perform measurement on the field. And the way we are doing it is to send atoms one by one through the cavity and detect the atom afterwards. The atoms are destroyed, but the photons in the cavity are not. We are in fact doing a version of the Einstein photon box experiment. Of course, the photon box is made by the cavity mirrors, and I will show you that the atoms which are crossing the cavity in many experiments are used in a kind of atomic clock, and we use information provided by the atoms to measure time. And in fact, when you have light inside the cavity, the rate at which this clock ticks is slightly changed, and we are measuring this change. So we are doing, in fact, two kinds of experiments. In one kind, the atoms are resonant with the cavity mode, and they can emit and absorb photons in the box. And we did many experiments of this kind. And in the second kind of experiment, we slightly detune the cavity from the atomic transition, so no photon absorption or emission can occur, but the atomic energies are slightly shifted by the interaction between the light and the atom, and we use this light shift to get information about the photons inside the cavity. For that, we need special atoms, which are called Rydberg atoms. They are very excited atoms in which one electron has been promoted to an orbit which is going much larger than in the ground state. So we start with an atom in its ground state, and using lasers and radiofrequency excitation, we just excite an electron on a very large circular orbit. This orbit has a radius of about 1/10 of a micron, which is 1,000 times larger than the ground state. So it behaves as a huge antenna, which is exceedingly sensitive to microwaves, as I will show in a moment. If you want to describe this atom using quantum physics, you have to use the Bohr's IDs. This atom is the electron going around the core is an electron wave, and the quantization condition is that you need to have an integer number of these wavelengths around the circumference. And in fact, the number of wavelengths around the circumference is called the principal quantum number of this circular Rydberg state. Here you have 51 such wavelengths. If you look at this picture, you also see that the electron can be delocalized anywhere on the circle, so that its center of gravity coincides with the nucleus, so you have no electric dipole. If you need an electric dipole, what you do is to admix the state E, which has principal quantum number 51, with in fact a wave packet, which will be centered at this point, and this wave packet revolves around the nucleus at 50 gigahertz, which is a Bohr frequency between the two states. So you see that what we are building here is a kind of classical atom, which looks like the atom of the old Bohr theory of 1913. And you can think of it as a planet revolving around the sun, as the early models of the atom were introduced, but also as the hand of a clock on a dial. And this is the image I will be using in the following. What do we detect in this experiment? In fact, we detect the atoms by ionizing them after they have crossed the cavity. And I try to explain on this slide the process of ionization and how it can be used to selectively detect the atomic state. You see here the Coulomb potential of the atomic nucleus, and you have here the two bound states, E and G, which are very close to the ionization limit of the atom. If you apply an electric field to this atom, it amounts to adding a linear potential, the slope being proportional to the electric field amplitude. And you see that now you will lower the energy barrier at one end to the point where the upper state will escape. So you will ionize the atom in this electric field. but the lower state is still bound. And if you want to ionize the lower state, you have to increase slightly the electric field to increase the slope. So what we do is that we apply a ramp of electric field, which increases linearly in time, and the field will reach at different times the threshold to ionize the upper and the lower state. So you will get now a signal which will tell you whether the atom was in state E and G, and you get a bit of information per atom, atom in E or atom in G, and this is the information you get from the atom about the field in the cavity. Just a brief summary of what we do when the atom and the field are resonant. We start, for instance, with an empty cavity, so the cavity is in vacuum, 0 photon, and the atom enters in the cavity in the upper state E. Then the atom will emit a photon and go to the lower state G. So you have 1 photon, and the atom is in a slightly smaller orbital state here. But of course, this is a reversible process, and at a later time, if the photon is not absorbed in the mirrors, it will be absorbed by the atom, which will come back to the upper state. And you have now what we call the vacuum radiosciation. The atom exchanges resonantly 1 quantum of energy with the cavity field. If you look at this process as a function of time, in fact, the system reversibly evolves into a linear superposition of E0 and G1 with amplitudes, which are the cosine and sine function of this Rabi frequency times the time. Now you can decide how long the atom interacts with the field. What you do is that when the atom enters in the cavity, you can apply a small electric field on the cavity mirrors to tune the system out of resonance very quickly. And so you can, in fact, control the time t. And you see that, for instance, if you control this time so that omega t is equal to pi over 2, you will have the cosine and the sine function will be equal. And what you prepare is a maximum entangled state. You have a system in which the atom is excited with 0 photon in the cavity and at the same time de-excited with 1 photon. The atom can leave the cavity, and now you have a situation of non-local entanglement, which was discussed by Alain Aspect this morning. So you can prepare non-local entanglement between the atom and the cavity field. If you do something on the atom and measure, it will have a direct effect on the field that you have in the cavity. I don't have time to discuss this kind of experiment, but you can use this entanglement between the atom and the cavity field to entangle several atoms with each other. They just cross the cavity one by one, and they exchange the entanglement with the cavity field so that the atoms get entangled and the field get back into vacuum. So much for the resonant case. And I would like now to go to the non-resonant interaction case and show you how we can count photons in the box without destroying them. You see a typical trace here showing how photons escape one by one from the box just because of imperfections in the mirrors. At some point, photons can be scattered out. And you see that the decay of the field in the cavity when you perform this measurement is no longer the classical exponential decay that you expect from classical electrodynamics, but it's a kind of staircase evolution which displays directly the quantum jumps of the light. So how does light delay the Rydberg atomic clock? We choose a cavity which has a frequency slightly different, detuning delta, between the atomic transition and the cavity mode. So in this case, the photons cannot be absorbed because energy conservation is not fulfilled, and the atomic clock is thus transparent. The atom will cross without absorbing the photons. But there is still an effect. The electric field, which is associated to the photons, slightly changes the rotation frequency of this atomic hand, which is rotating around the core. And this change in frequency is called a light shift effect. I don't have time to discuss it in details, but I can schematize it here. You see here the cavity mode. The atoms, of course, it's not to scale. It made it very big. And here is the electron. And this electron is subjected to 2 electric fields. One field is just the Coulomb field of the nucleus, whose order of magnitude is 10 to the 5 volt per meter for this big Rydberg atom. And the other field is just the vacuum field of the field of a single photon. that you compute by just taking the energy h nu of a photon, divide by the volume of the cavity, and you take the square root of that, and you find 1 millivolt per meter. So you see that the electric field of a photon is about 100 million times smaller than the Coulomb field seen by the Rydberg electron. But this very small effect is big enough to be detected by an atomic clock, which is, of course, very sensitive to perturbations. During the atomic transit time across the cavity, which lasts about 30 microseconds, the hand makes about 1.5 million turns around the core, and one photon can shift this phase by half a turn. So about an effect of the order of 10⁻⁷. Another way to look at it is to look at the light shift of the level E and G. And I remind you that the light shift effect was discovered by Cohen-Tanuji, who was my thesis advisor back in 1961. You see here the two states E and G. As the atom crosses the cavity, E is light shifted upwards, G downwards. And you see that the frequency of the transition is changed by an amount proportional to the photon number and inversely proportional to the detuning. And in fact, so this shift is proportional to n, where n is the photon number, and the phase shift per photon can reach the value pi. And so what you have to do is just to look at what happens when the atom has crossed the cavity. If for instance, you have 0 or 1 photon, the phase of the dipole will point in one direction if there is 0 photon, in the opposite direction if there is 1 photon. And to measure this phase shift, you need, of course, an interferometer. And you perform what is known as a quantum non-demolition or a QND photon counting. So what is the interferometer? It's a standard interferometer which was developed by Norman Ramsey back in the early 1950s. You see here the cavity which contains the field that we want to measure. In this box, the circular states are prepared, and they cross the main cavity one by one, and then downstream an electric field is applied, and we detect the atom in E or in G. We get 1 bit of information per detected atom. Two very important ingredients are these two auxiliary cavities, R1 and R2, one before the atoms cross the cavity and the other one after. In this first cavity, a pi/2 pulse of microwave is applied to prepare the state superposition. It is as if we were starting the atomic clock at this point. Then the atomic dipole rotates, and a second flash of microwave is applied downstream to detect the phase accumulation. And this succession of two separated oscillatory fields is what is used in all atomic clocks, cesium clocks, for instance, to measure time. And the only difference here is that we have a very bad atomic clock in the sense that it is very sensitive to perturbations, and we can measure light intensity in this way. So when you tune, if you tune the frequency of the Ramsey zones, you see the typical Ramsey fringes, which result from an interference effect. And mathematically, these fringes are quite similar to the fringes of a Young double-slit interferometer. And if you have tuned your system properly, you will see this kind of fringes if there is 0 photon in the cavity, and fringes which are shifted by half a fringe interval if there is 1 photon. So if you tune your interferometer at the maximum of the fringe for 1 photon, you will be at the minimum of a fringe for 0 photon, which means that as soon as a single atom has crossed the system, if you detect the atom in one state, it means that there was 0 photon in the cavity. In the other state, that there was 1 photon inside. So where does this photon come from? In fact, we get it for nothing, because we can use the blackbody radiation background. Our experiment is at a very low temperature, 0.8 Kelvin, and at this temperature, at 50 gigahertz, the field is fluctuating between 0 and 1 photon. 95% of the time, the cavity is empty, and 5% of the time, 1 photon pops in due to thermal fluctuations in the cavity mirrors. So we just have to send atoms one by one. We flash the Ramsey zones, and we detect the atom. And what we expect to see is this kind of correlations. The atoms, a long string of atoms is detected in state G, then in state E, in state G, in state E. And so you see that you have high-order correlations between the atoms, which are produced by the field in a quantum non-demolition way. And you see here a real experimental signal. This is this kind of signal, if you expand the time scale, you see the exact time at which the quantum jump occurred. And you see also that for a very long time, half a second here, hundreds of atoms see the same photon inside the cavity. You might ask how comes that you can see the field for half a second, and I told you that the lifetime of the cavity was 1/10 of a second. This is, of course, due to the fact that the distribution of the lifetime of the photon is exponential, and so in the tail of this exponential function, there is a small probability that some photons will survive many lifetimes, and of course, I choose one of these photons here. It's the distribution of lifetimes of photons as all quantum particles is completely different from the distribution of lifetimes in a population. Of course, we know that in a population, nobody has lived 5 average lifetimes. So I don't think it would be better for us to have this kind of distribution, because the highest probability to die is at the time t equals 0. So it's much better to have a kind of flat distribution with a sharp tail than to have this kind of long exponential tail. But of course, all these measurements are in complete agreement with quantum electrodynamics. I also want to mention that this can be, of course, discussed also as a quantum gate. The state of the field, 0 or 1 photon, is controlling the state of the atom, E or G, and you can also perform entanglement experiments in this way. For instance, if the photon is in a superposition of 0 and 1, a long stream of atoms will be in a superposition. 0 will be correlated to G, 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 and 1 will be corrected to E, 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 and we get a massive entanglement between the field and an ensemble of atoms crossing the cavity one by one. How can we count larger photon numbers? First of all, we have to introduce in the cavity more than 1 photon. And we can do that very easily by just having a horn coupled to a microwave source, classical microwave source, and we send a pulse of microwave in our system. And a few photons will be scattered off the edges of these mirrors inside the cavity mode, and you see that you will build up a field inside. Then you switch off the source. What I want to stress is that the field that you build in this way does not have a well-defined photon number. Again, because of Heisenberg uncertainty relations. This classical source produces a field which has a well-defined phase, and if the phase is well-defined, the amplitude or the photon number cannot be. And so we prepare a superposition of photon number states with different values of n. Once you have prepared this field, you switch off the source, and you see that it takes some time for the field to decay. So you have about 1/10 of a second to perform measurement before the field has decayed, and you measure with atoms crossing one by one this field. And this explains why you need a very good cavity, because you must be able to send hundreds of atoms before the field has decayed. I just show you on this slide the result of a real experiment. At the beginning of the experiment, we are in a superposition of all photon numbers. We don't know what is the photon number in the cavity. And then we send atoms one by one, and each atom provides 1 bit of information about the field. And from the result of the atomic measurement, we can infer what we have learned about the field according to a classical statistical inference, which is called Bayes' law. So in fact, this is just a classical inference produced by the information that we are accumulating. And I will show you here how this probability distribution evolves in time. You see, as atoms get detected, the photon number distribution changes randomly because the events are random. But after a few tens of atoms have crossed the cavity, 1 photon numbers take over. So it's a kind of horse race whose result is random. But in the end, you get a photon number. And I must stress that according to the laws of quantum measurement, the photon number was not there before the measurement. Before the measurement, you were in a superposition state, and the photon number emerges through the interaction between the atom and the stream of, between the cavity field and the stream of atoms crossing the cavity one by one. Here we found the result 5, but if you do the experiment again, you will find something like 3, 4, 2, 0, 1, and when you have done a lot of experiments, you reconstruct the histogram of the coherent field in the cavity, and we find that it has a Poissonian shape as predicted by Glauber back in the 1960s. So this experiment illustrates quantum measurement postulates about statistics. We can also perform longer measurements, and you get this kind of histograms. At first, the field collapses into a given photon number. Then, if you keep measuring, the photon number remains stable. This is, again, a postulate of quantum physics, and it reminds us of the kind of postulate that Boris Rodriguez was talking about. Once you have measured a polarization, if you keep measuring, you find the polarization. And this is true until perturbations get into play and station. So you see that after a while, the photon number will decrease randomly, and you will see these quantum jumps bringing the field back to vacuum. And this is just a single trajectory. To conclude, I would like now to discuss the Schrödinger cat experiment. Up to now, I could discuss the experiments by using the particle aspect of light. I was counting photons in a box, but the phases of the amplitudes between different photon numbers did not matter. Now I would like to describe an experiment in which the phase is important, and I would like to describe what happens to the phase of the field when one atom crosses the cavity. So instead of looking at the phase of the atomic dipole when this dipole is coupled to a field, I look at the opposite problem. What is the phase of the field after it has interacted with a single atom? So you see here the standing wave of the field in the cavity. One atom is crossing in the center of the cavity here, and as I told you before, the energy of the atom field system undergoes a light shift, which has a Gaussian shape because the transverse profile of the mode is Gaussian. So this means that when the atom enters in the cavity, its kinetic energy is increased in a transient way, and this is exactly the kind of atomic force effect which is used in all laser cooling experiments. When the laser beam is non-resonant, you get a light force, which is the kind of force which were discussed in the optical tweezer papers that we heard at the end of this morning. But the difference here is that this effect is very tiny, and we are looking at these forces at the quantum limit when there is only 1 or 2 photons left in the cavity. So you see that if you have n photons, the energy shift will be proportional to n, delta E1 being the energy shift per photon. Now I ask the question, where is this energy coming from? Where is the kinetic energy coming from? It can come only from the field, and it can come from the field in 2 different ways, either because the photon number has changed, but this is impossible because the atom and the field are non-resonant. So the only other way is because the frequency of the field of each photon has changed, going from omega to omega minus delta. And if you have n photons, you get a loss of energy, nh bar delta. This is an index effect. Each atom crossing the cavity slightly changes the frequency of the field inside. And since this is because it's like a small index of a fraction going in, and it changes the wavelength. The wavelengths cannot change because it's linked to the boundary condition. So the only possibility for the field is to slightly change its frequency. Then we apply energy conservation, and we find that the frequency shift of the field produced by one atom is equal to the energy shift of the atom on the atom produced by one photon. So it's a very simple result, which means that when the atom crosses the cavity, the phase accumulation can be of the order of pi. So you can have a large phase accumulation. And the other very important feature is that the sign of this effect depends on the atomic state. The upper and the lower state of the transition will give rise to a phase shift in one direction or in the other. And this is what is at the heart of the Schrödinger cat experiment. Before describing the experiment, I have to give you, to remind you of the way we can represent an oscillating field in a very simple mathematical form. You see here 3 classical waves which have the same frequency but which are 120 degrees out of phase with respect to each other. So one important parameter is the amplitude, the other one is the phase of the field. And we know, at least from the time of Fresnel, 200 years ago, that this kind of oscillation is represented in the complex plane by a vector, whose length is proportional to the amplitude of the field, and the direction of the vector gives you the phase. For instance, these three fields, which are 120 degrees out of phase, are represented by three vectors with a 120-degree angle between them. This is a classical picture. What is a quantum coherent state? It's exactly the same picture, except for the fact that the tip of the vector is now fuzzy because of Heisenberg uncertainty relations. So we have a superposition of different photon numbers, which gives this fluctuation, and a small fluctuation, conjugate fluctuation in the phase. And the tip of this vector is now distributed along a Gaussian function, which is represented here in coded colors. And this representation is called a Wigner function. I don't have to enter into details, but it's a kind of photography of a coherent state. It's just a Gaussian function in phase space. So what happens to this Gaussian function if one atom is crossing the cavity? And again, we use a Ramsey interferometer. Before the atom enters the cavity, we prepare it in a state superposition. Then it crosses the cavity. And you see now that one state will be associated to one phase shift and the other state to the opposite phase shift. And this is again exactly the Schrödinger cat situation. We have one atom which is correlated, which is entangled with a field which can contain many photons taking different phases. If you detect the atom at this point, you will project the field with this phase or that phase, which is not very clever. What we want to get is the Schrödinger cat. So what we do is that we send the atom to the second Ramsey zone, which mixes again the state E and G. And now, when we detect the atom here, we can no longer know in which state was the atom when it crossed the cavity. So it maintains the cat's ambiguity, and detecting the atom now and finding it in E or G projects the field into a cat state superposition. First of all, I want to say that this experiment is a demonstration of complementarity. If you look at what happens to the atom which has crossed the cavity, the atom has undergone 2 pi/2 pulses which have mixed states E and G. So it looks like an interferometer, a Mach-Zehnder interferometer, in which you have, in Hilbert space, 2 passes for the atom to go from this state to that state. It can follow either this state or that state. So you can think of the Ramsey zones are kind of beam splitters for the internal state of the atom. But now you see that the atom is not alone in this game. The field in the cavity is a kind of spy, which will take 2 different phases depending upon whether the atom crossed the cavity in E or in G. So it looks very much like the Einstein movable slit experiment. The field in C behaves as a meter, which provides information about the path exactly in the same way as the beam splitter, the slit here was telling us the path in the Young double slit interferometer. So what we do is that we sweep the frequency of these Ramsey zones, and we look at the probability for the atom to go from one state to the other, and we get fringes. But you see that the contrast of the fringes depends upon the overlap of the 2 Schrödinger cats, the 2 components of the Schrödinger cat. And we can change this overlap by just changing the detuning between the atom and the cavity. And this way, we already illustrate Bohr's complementarity in an experiment which is very similar to, in its principle, to the movable slit experiment. So this is what we get with a single atom. But then what we can do is to send other atoms in the cavity and use these atoms to reconstruct the Wigner function of the cat. What we have prepared is a state in which the phase of the field can take 2 opposite values. And this is a superposition of one phase and the opposite phase, the 2 phases being at once in the system. This state is quite different from a statistical mixture in which we would have one phase or the opposite phase in a classical logical way. So in the first case, you expect to see a Wigner function like this. The 2 coherent states are these Gaussian bumps here. And in between, in the Wigner function, you should have fringes which express the fact that you have a quantum superposition. And this is quite different from the statistical mixture in which the fringes are lacking. So in one case, you have a quantum state. In the other case, you have a classical state. And the only way to tell the difference is to measure the Wigner function. And what you expect also to see is that this Wigner function will evolve very fast from the left to the right picture because of decoherence. So non-classical states are in fact characterized quite generally by these negative values of the Wigner function, and decoherence destroys very quickly these quantum features. So I will not enter into details, but what I want to say is that when you count photons, what you do is that you measure the probability to have different photon numbers, which are the diagonal elements of what is known as a density operator of the field. It's just a matrix with the photon numbers in the row and columns, and what we have measured by QNT measurement are the diagonal elements. But if you want to reconstruct the Wigner function, you need also the off-diagonal elements. And the recipe to determine them is to translate the field in phase space by adding coherent states and making measurement of the photon number in all these translations. And this is called quantum tomography, because it's very similar to the tomographic methods used, for example, in medicine to reconstruct the internal state of a body by making X-ray measurements. So I don't have time to enter into these details, but in the end, when you have sent many, many atoms and made many, many state translation, you reconstruct this cat state with a live and dead cat and the quantum interference in between. This is a small cat which contains only 2 or 3 photons on average, but we can get larger cats, as I will say, to conclude. What is decoherence doing? What is the decoherence in this case? This is a Schrödinger cat, a superposition of 2 phases. But of course, this cat is interacting with the environment. In this case, the environment are the empty modes of the field, which are coupled to the cavity field via scattering through mirrors imperfections. So at the beginning, this environment is in vacuum, but very quickly, photons will leak into the environment, giving rise to 2 states, which will very quickly become different. And as soon as these 2 states become different, they play the role of the spy in a complementarity experiment. So you get information about the state of the field by looking at the environment, and you don't have to look. The mere fact that this information is there is enough to destroy the fringes. In fact, we do it, we observe it by just preparing the cat state and then letting the system evolve and measuring after a delay the Wigner function. And by adding snapshots with increasing delays, we get this kind of movie, which shows that after a time which is of the order of 1/10 of the damping time, about 10 to 20 milliseconds, the fringes are completely washed out. So you don't see fringes anymore. And of course, this is in complete agreement with a theory of decoherence, notably the one which was developed by Wojciech Zurek about 25 years ago. So I think it's time to conclude. I just want to say that the systems we are studying are not very practical for quantum information applications, but now there is a field which is developing very fast in solid-state physics, which is called circuit QED, in which the Rydberg atoms are replaced by a superconducting circuit containing one or several Josephson junctions. This circuit has quantum levels, and you can isolate a 2-level system in them. And you can couple this 2-level system to a strip-line cavity or to a 3-dimensional cavity, which is superconducting and has a very high Q. And you can couple microwaves directly to the qubit or microwaves inside the cavity, which plays the role of our Ramsey pulses or feeding into the cavity. And with these experiments, you can produce Schrödinger cats. This is a Schrödinger cat in circuit QED, which looks very much like the cats we are producing. This is an experiment which was performed 7 years ago. Since then, circuit QED has improved a lot, and now they can build up cat states which have 100 photons or even more. The systems are reacting much faster because these Josephson junction circuits have an electric dipole which is orders of magnitude larger than the Rydberg one. So the Rabi frequency is much faster, and these systems are certainly much more practical if you want to apply them to quantum information. So I conclude by saying that we have come a long way since Bohr's atom and Einstein's photon box. And you see here 2 covers which are only 4 years apart, and which show that in 2007, cavity QED with Rydberg atoms were way ahead, and something like 4 or 5 years later, the circuit QED has caught up by shuffling photons between these artificial atoms and these cavities, you can perform gates and play a lot of quantum games. So far, factoring something like 15 has been demonstrated, and a lot of progress is being performed in this direction. So I think it's time to conclude. I just want to acknowledge my co-workers in these experiments, which have, in fact, I have described to you something which has started, a series of experiments which have started more than 20 years ago, and the collaboration with Michel Beaune and Jean-Michel Raymond, who have been my students and became my co-workers, has been really essential, and would have been absolutely unable to achieve all this without working very closely with them and with all the students and postdoc we have had over many years. This was the group a few months ago at Collège de France, and I want to stress also Igor Dotsenko and Sébastien Glaise, who are junior permanent member of the team. And I will stop at this point, and thank you.